And hello YouTube, welcome to this video. So the last video we talked about the SRK equation. So today I want to talk about the Peng-Robinson equation. So just want to go through some quick resources first, where you can find more information about it. First of all, LibreTexts is a great option. You just go to chemical engineering, go to phase relations in reservoir engineering. You will find stuff inside, I think, cubic EOS and their behavior. I think chapter 10 or 11. Can't remember exactly which one it is. You can go and take a look at it yourself. Of course, this is a very short chapter. Plus, you can look online as well. If you have access from your university or your research institute, whatever it is, you should be able to have some access to Science Direct, Elsevier, whatever it is. Yeah, so things like this, Peng-Robinson equation of state, 40 years through cubics, or cubic equation of state. Now, if you have a textbook, which is what I'm going to refer to today, I would use that as well. So these are the three sources of information. Of course, the first one I introduced to you is LibreTexts because you can get it for free. I know it's important for you to be able to get the information without paying a bomb for it. Okay, so without further ado, let's start on the Peng-Robinson equation of state. For this, something I want to increase my font size to maybe 18 or VS Code. Close, yeah. So that at least you will be able to see a little bit more. Then I think I'm going to do some nice things to help justify this equation, or rather justify the text here, and of course have nicer fonts. Now to do so, text or tips has a very nice way you can make your document look a bit more like LaTeX. It's very nice. I like to take some of these, like the text is computer modern, and of course the justification is being true. So let me change the fonts first. Okay, you can see immediately how this starts looking a little bit more like LaTeX already. Okay, so that's one. I'm gonna set the justify. Okay, and of course I actually want to turn off my settings. I'm gonna turn off text wrap. Word wrap is off. Okay. Okay, I keep forgetting. Alt-Z toggles word wrap. I'm gonna toggle it off. Okay, so I'll just save this and get justification through, and look, it's a lot nicer now. So let's start with the Peng-Robinson equation of state, and maybe some background for it. So let me do this first. Van der Waals, SRK EOS, and I'll have it over here. Then I will have Peng-Robinson. Okay, Peng-Robinson EOS. Okay, so again, I'm going to add my references here. So some historical background as usual. Okay, so this is how you do the text wrapping thing. Some historical background. If you take a look at this article right here, you will notice that the Peng-Robinson equation of state is specially catered to oil and gas. Okay, it's focused a lot on the oil and gas industry. So if you are dealing with organic molecules, okay, organic molecules, and also stuff like hydrogen sulfide, and some inorganic gases like nitrogen, oxygen, hydrogen sulfide, Peng-Robinson equation or state is quite suitable. So let me just write that down so don't forget. Okay. Let me also put my bibliography here. Okay. So Peng-Robinson equation of state. I'll of course get the other bibliography here. Cite this big tech. Yeah, there you go. Okay. Sandler, chemical thermodynamics. So PREOS, the Peng-Robinson EOS, otherwise known as PREOS, is an equation of state. Again, I'll put EOS here. Meant for oil and gas industry use. It's okay. So just let me see this. Okay, the Vin key doesn't work. Lopez 200217. See whether this works. Yes, so I have the, yeah, it's meant for the oil and gas industry. It is used for molecules such as hydrogen, sulfide, oxygen, nitrogen, and several hydrocarbons. Okay, I'm gonna cite Sandler's here because that's what it says. Okay. At Sandler's, okay, at Sandler's, Sandler 2017 chemical, okay, and of course I'm gonna also cite the reservoir engineering. Okay, so I'm gonna go back to bib. Okay, I'm gonna put this here. Paste. Okay, so all the citations are done. So yeah, it's used for molecules such as hydrogen sulfide, oxygen, nitrogen, and several other hydrocarbons. So the form is as such, or the equation is as follows. Okay, so I'm going to copy and paste and edit as usual. Okay, note that some things are the same as a SRK equation of state. Some things are not. Okay, so one of the things we are going to modify from the SRK equation of state is this volume term right here. So instead of just this, V and V plus V, okay, we're going to add another term right here. Okay, because again, we do not want this attractive force going to infinity. So we have more than this volume cofactor term right here. So I'm going to change that. I'm going to change that. So this first V term, or rather, yeah, this first V term is going to be only part one of the Peng-Robinson equation of state. We're going to add another term here. Okay, that term will happen to be as follows. You have a B and tilde V minus B. Okay, so this is, I guess, to ensure that the volume never ever reaches zero, because if B tends to zero, well, I guess this thing here will be negative. If B tends to zero, this thing here will be negative. So it's just it's a non-zero term, I guess. That's a non-zero term. No matter what happens at the bottom, you're probably not gonna get zero, if I'm not wrong. Okay, but yeah, I'll just leave it be like that. Okay, so we have a V minus B term here. This does not change. this RT does not change, but this A term here, well, this temperature dependent term for the for this Peng-Robinson equation of state is going to change. So these two things here, this A and alpha, we are just going to combine into a A, and it's just a function of T. So no more alpha right here. We just have an A of T here. So I'm going to have the A of T equation changed. Okay, so this A of T equation is changed here. Okay, and it's going to be, yeah. You still have an alpha term, but it's slightly different. So let's have the A of T term right here. A, or rather I'm going to put this here. A of T. So this is explicitly a function of temperature. You will have a different number here. Again, it's empirical 45724. Okay. The R squared TC squared over PC is the same. Okay. So the next thing here is you have an alpha of T. So alpha of T. So you're going to have a big alpha T there. This alpha T in itself is going to be a function of the reduced temperature and the eccentricity factor. Okay. So yes, alpha T will still be the square of this whole term here. So 1 minus T, the reduced temperature. Okay, 1 minus reduced temperature. This M here will stay inside, this 1 will stay inside. So it's pretty much similar. However, the term over here, this M term here, sometimes it's in literature known as kappa. Just keep it as M. Okay. Or rather, okay, maybe let me change it to kappa maybe, because that's what is in the textbook. Okay. So whatever this is, whatever this form is, this is the eccentricity factor form. So I'll just leave it, I'll just try to keep it consistent with the textbook. Okay. Okay, 37464. Okay. 154226. And here will be 26992 omega squared. So this is just a slightly different expression for A. You have a different expression for this AT here. All right. And what else? B is also slightly different. Okay. So you still have the R, TC, and PC right here, but this number right here is 0.07780. So this is essentially the Peng-Robinson equation of state. All right. Now, if you actually look in literature, there'll be several updates to this equation of state. There'll be several updates to this equation of state, but we won't be talking about them. This is pretty useful as it is. Okay, in its present form, it's still pretty useful. So this is sort of the form that we have from ideal gas, PV equals to nRT. Okay, PV equals to nRT. Let me just centralize this a little bit. Now PV equals to nRT, you divide by n, you get this molar volume. You got it expanded through van der Waals, and then SRK, the Rayleigh-Kwong equation sort of expanded on it, and then you got Soev-Rayleigh-Kwong as well. Rayleigh, I'm sorry, I don't know how to pronounce the name properly. And then Peng-Robinson applies, sort of changes the SRK equation of state and fits it very nicely to the hydrocarbons. Okay, so this one is pretty good for hydrocarbons. This one is good for sort of anything else. So it's not a one size fit all. Right? Again, why are these sort of equations like that? it's because, I mean, why are the numbers like that? These are just data fits, polynomial data fits again. So there's no so-called rocket science in that regard, though the way these parameters scale with the critical temperature and pressure is pretty much the same. So I'm gonna just stop here. This is enough background for us to go to more other things, like, well, actually program this in. Yeah, we want to actually program this out. So I'm gonna stop here, and maybe we'll continue more in the next video. Thank you.